Here is a pile of data with a secret. Customer locations, pixel colors, feature vectors. Whatever they are, we get only the coordinates. No labels, no answer key, nothing telling us what belongs with what. Just points on a plane. And yet, your eye does something instantly. It sees two natural huddles, a clump on the left, a clump on the right, with a gap between them. Finding that hidden grouping, with no labels to guide you, is called clustering. This is unsupervised learning. Nobody hands us the right answer, so the structure has to come out of the data itself. And the most famous algorithm for it is beautifully simple: k-means. Before the algorithm, let's be honest about the goal. We want k clusters. Each cluster gets a single representative point at its heart, called a centroid, written mu, and every data point belongs to exactly one cluster. What makes a grouping good? A tight one. Points should sit close to their own centroid. So we measure the total squared distance from every point to its centroid. This is the within cluster sum of squares, or WCSS. In plain words, for each cluster, add up the squared distance from every point to its centroid, then add those totals across all clusters. Small WCSS means tight, well-separated groups, so the whole task is one clean sentence. Choose the clusters and their centroids that make WCSS as small as possible. Everything k-means does is chasing that one number down. Minimizing that directly is brutally hard. You'd have to try every possible way to split the points. So k-means does something cleverer. It alternates to easy steps over and over and lets them do the work. It's a dance in two moves. Move 0. Initialize. Just drop k centroids somewhere on the plane, even at random. They'll start in the wrong spots, and that's fine. Move 1. The assign step. Hand every point to whichever centroid is closest. This paints the plane into k-colored territories. Move 2. The update step. Each centroid now owns a set of points, so slide it to their mean, the true center of its own cluster, and move 3. Repeat 1 and 2 over and over. When a full pass changes nothing, no point switches, no centroid moves, you've converged, and you stop. Now the payoff. Let's actually watch it run. Same 8 points in gray, because we don't yet know their groups. I'll drop 2 centroids in poor starting spots on purpose. A gold cross down here, a teal cross up here. Step 1. Assign. Each gray point flies to the color of its nearest cross. The 3 points closest to gold turn gold. The other 5 closer to teal turn teal. That's the first split. And the running cost, WCSS, is 36. Step 2. Update. Each cross now glides to the mean of the points it owns. Gold slides up into its little cluster, teal slides right toward the bigger clump. The centroids have found better homes. Now round 2. Reassign against the moved centroids and watch the point that sits between the two groups. It was teal, but gold is now genuinely nearer, so it flips to gold. 1 point changed its mind, and the cost drops sharply to about 9.8. Update again. The crosses nudge to their new means, only a touch this time. Round 3. Reassign once more. And this time, nobody moves. No point switches color. No centroid budges. When a full pass changes nothing, the dance is over. K-means has converged, with the two clusters cleanly separated. Let's do a full round with real numbers, so nothing hides. 4 points, and 2 starting centroids. mu1 at 1, 1, and mu2 at 5, 5. In k-means, we compare squared distances. Same nearest answer as ordinary distance, but no square roots to slow us down. Assign step. Take x1 at 1, 1. Its squared distance to mu1 is 0. It sits right on it. And to mu2, it's 32. Closer to mu1. So x1 joins cluster 1, x2. 1 versus 25. Cluster 1. x3. 25 versus 1. That one's cluster 2. And x4. For T1 versus 1, cluster 2 as well. So the left pair goes to cluster 1, the right pair to cluster 2. Now the update step. Cluster 1 holds 1 1 and 2 1. Cluster 2 holds 5 4 and 6 5. Recompute each centroid as the coordinate-wise mean. For cluster 1, average the excess. 1 plus 2 over 2 is 1.5. And the ys, 1 and 1 average to 1. So mu1 moves to 1.5. 1 for cluster to the same way. 5 and 6 average to 5.5, 4 and 5 average to 4.5. Mu2 moves to 5.5, 4.5. One assign, one update. That is a single k-means iteration done by hand. Here's the quiet guarantee that makes it all work. That update never made things worse. Let's prove it on the very same clusters by measuring WC's S before and after we moved the centroids. Before, with the centroids at their old spots, cluster 1 contributed 0 plus 1, cluster 2 contributed 1 plus 1, a total WC's S of 3. After sliding each centroid to its cluster's mean, recompute. Now cluster 1 gives a quarter plus a quarter. Cluster 2 gives a half plus a total of just 1.5. The cost fell from 3 to 1.5. And that's no fluke. The mean is, by definition, the point that minimizes squared distance to a set. So the update step can only lower WCSS, never raise it. The assign step can only lower it too. Every single move shrinks the cost, or leaves it flat. But here's the catch hiding in that guarantee. The cost only ever goes down, so it must eventually stop. With finitely many ways to group the points, k-means always converges. The trouble is what it converges to. Picture the cost as a landscape of hills and valleys. K-means always rolls downhill, but it rolls into the nearest valley, not necessarily the deepest one. Start it here, and it settles into this shallow dip, a local minimum. Good, but not the best clustering possible. A different start would have rolled into the deep valley on the right, the global minimum, the genuinely best split. So the answer you get depends on where you begin. Initialization isn't a detail, it decides the outcome. So in practice, you never trust one run. Two fixes. Restart many times from different random seeds and keep whichever run ended with the lowest WCSs. Or use k-means plus plus, a smarter seeding that spreads the initial centroids far apart, usually landing you in a much better valley on the first try. One question we've dodged: K itself. K-means needs you to tell it how many clusters to look for. Pick too few and you fuse real groups together. Too many, and you shatter one group into fragments. So how do you choose? The elbow method. Run k-means for a range of k values. Record the final WC's S for each and plot cost against k. More clusters always means lower cost. At k equal to the number of points, it hits 0. So the curve only ever falls. But look at the shape. From 1 to 3, the cost plummets. Each new cluster explains a lot. After 3, it barely improves. The curve flattens into a gentle slope. That sharp bend, where steep suddenly becomes shallow, is the elbow. The elbow is your sweet spot. Here, k equals 3. Past it, you're paying in complexity for almost no gain. It's a judgment call, not a formula. But the bend usually points straight at the number of clusters really in the data. Your turn, two quick tasks. First, a point Q at 3. 3. Does it belong to centroid A at 2? 2. Or centroid B at 6? 4. Second, 3 points sit in a cluster. What's their new centroid? Pause, work both out, and I'll wait. Part A squared distance from Q to A. 1 squared plus 1 squared is 2. 2b. Minus 3 squared plus minus 1 squared. 9 plus 1, 10. 2 beats 10. So Q joins cluster A. It's clearly nearer. Part B. The centroid is the coordinate-wise mean. Average the excess 2 plus 4 plus 3 over 3. and the y's 2 plus 3 plus 4 over 3. Both come out to 9 over 3, which is 3. So the new centroid is 3, 3. If you got both, you've got k-means cold. Trap 1. Forgetting that you own k. K-means will carve the data into whatever number of clusters you ask for, sensible or not. It never discovers k on its own. Use the elbow. Trap 2. Trusting a single run. Because it only finds a local optimum. A bad initial seed can leave you in a poor split. Always restart several times, or seed with k-means plus plus. Trap 3. Skipping scaling. K-means measures squared distance. So a feature with a huge range swamps all the others and hijacks every cluster. Standardize or normalize before you cluster. Always. And trap 4. It's shape bias. K-means assumes clusters are roughly round and similar in size. Give it long stringy shapes, rings, or wildly uneven groups, and it splits them wrong. Reach for a different method there. Let's tie it together. K-means chases one number, the within cluster sum of squares, the total squared distance from points to their own centroids. Make that small. It gets there with a two-step dance. Assign every point to its nearest centroid, then update each centroid to the mean of its points, repeated until nothing changes. Because each step only ever lowers the cost. It always converges, but into a local minimum, not guaranteed the global best. So the starting point genuinely matters, and two knobs are yours to set. Choose K with the elbow, and give it a good start with restarts or k-means plus plus. Get those right. And this simple dance will find the hidden structure in your data, with no labels at all.